The purpose of this lab was to determine the voltage drop and current at different parts of resistor circuits, and also to determine the charge and discharge properties of resistor capacitor circuits. Some models used were Watt's law, P equals IV, node and loop rule, and capacitive charge and discharge equations. The results of this lab were determining such. The RC circuits with higher resistance take longer to charge and discharge. Series resistors with higher resistance cause more current drop, and lower resistance with equal voltage leads to higher currents. Some fundamental physics models used were Watt's law, as discussed before, which is P equals IV. These equations can be used to determine current and voltage, considering the power, and these can be used interchangeably. The node and loop rule were that at any round trip point, total change in current needs to equal 0, and node rule is that any current leaving a node must equal the current entering that node. The capacitor discharging charge equations is described below, but the main takeaway is that it is an exponential growth or decay function, which leads to some of the properties we will see later. The experimental setup is shown below. It is two 1.5 volt batteries connected together, and then a capacitor connected through a resistive lamp, which will glow when current is passing through. The results for the experiment start as such. With the two batteries connected to ammeters, switched to ammeter mode, and a 4.7 ohm and 100 ohm resistor connected as such, the current measured in the first ammeter is 17.2 milliamps. The voltage drop in the first resistor is 0.811 volts, second resistor 1.69 volts, and the last ammeter 17.1 milliamps, showing that current tends to stay the same, but voltage drops depending on resistance. The experimental results can be continued as such by creating a diagram of the drop in voltage. You can see that it drops to 0, and it drops based off of the resistance applied. The ammeter will have some voltage drop because there is some resistance in the measuring circuit behind the meter. Continuing with the lab, some other results. When the bottom ammeter was disconnected and then shunted the 47 ohm resistor, the current jumped up to 38 milliamps and 36 milliamps. These can be considered the same because of small measurement errors. The reason this current jumps so much is because most of the current goes through the ammeter that is shorting out the 47 ohm resistor instead of going through that 47 ohm resistor, meaning that more current can pass through because overall resistance is lower. In the second layout, with the charging and discharging of a lamp through a capacitor, when the lamp was 20 ohms, it took 45.25 seconds to charge and 15.5 seconds to discharge through the capacitor through that lamp, measured as when the lamp turned off during charging and turned off during discharging, signifying that no current was flowing through the circuit. For the 10 ohm lamp, the charge times and discharge times were lower at 9.13 seconds and 12.26 seconds for each of those two values. Some sources of errors were that the measurement times may not have been precise because they were visually performed on a lamp, so it was a little arbitrary, and the resistance of those lamps may not have been perfect. It's also multimeters have some shunt resistance when in mode, so they can act as resistors as well as measurement devices and will interfere with the currents in the circuit. The main discussion question that we must focus on is what if one charged a capacitor with no resistor in the circuit? In an ideal model, this would charge instantly because the exponent to E for the charging equation would end up going to 0, so E would become 1 immediately, and the current would immediately become the input current. This does not happen ideally because there is some resistance in the current. There's some limits to the amount of power in terms of amperage that the batteries can provide, and there's also some resistance in between there's like some current that can pass through the plates of the capacitor, which means that the capacitor will act as a resistor as it charges more and more and lead to non-ideal behavior, meaning that the ammeter will never fully stop passing current and the time cannot be fully measured. When we did measure it, we went for 2 or so minutes and still measured some change in the current of the ammeter over time. So you define that this will never reach a truly steady state where we can stop the measurement.